This video is going to cover limits number 11, questions 34 through 44, so the end of the review. 34 and 35 deal with limits number 7, which was the properties of limits. And you see, first of all, I added something to the question that is not on your review if you've looked at it. And I've added that f and g are continuous functions, and we need that mostly when we get to number 35. So number 34 is just going to use the properties that are just pretty basic and they're very intuitive. If you're doing the limit of a sum or difference, then you just do the limits independently. And the same with a product. So the limit of a product is just the product of the two limits. So I'm going to apply these two properties on number 34. So you see, all I've really done here is just done the limit as x approaches 0 of each one of these functions, and I've kept the operations between them the same. And now I just look at the given information. See, limit as x approaches 0 of f of x is 8, of g of x is negative 5, and I just plug those limit values in. And then when I just do all of these calculations, I end up with a final answer of negative 35. When I first look at question 35, what I see is I have a composition of functions here. F of g of x, so g of x is being plugged into f of x, so we call that a composite function. And I have a rule for that. My composite rule says the limit as x approaches c of f of x is f of the limit as x approaches c of g of x. In other words, I have to do the limit as x approaches c of just the inner function. And I can see the limit as x approaches 0 of g of x is part of my given information, and that value is negative 5. So this equals negative 5. And now my next move is to do f of that value. So now some of the restrictions on this is that my function f has to be continuous at this particular value. And now you see why I needed to add that given information at the front end of this problem, because I need f to be continuous at negative 5 in order to finish this problem out. So I just do f of negative 5, and I've already verified that continuity, and I see that that value is 3. So my final answer to the problem is going to be 3. Here's question 36, and as you see, we have another composite function, so I'm going to use that same composition rule. So my first order of business is to find the limit as x approaches 2 of g of x. And what I see in my g of x graph is as I approach an x value of 2, whether I come from the left or from the right, I'm heading for that same y value of 2. So my answer to the limit is 2. It is irrelevant that this function's undefined at 2 because all I need is for the limit to exist, and it does, and its value is 2. My next move is to do f of this 2 right here. But what I see on the graph of f is that at the value of 2 right here, I do not have a continuous function, and that was the requirement to use this rule, which means I cannot use the composite rule. I've got to find some other way to evaluate this limit. So my little workaround is to see how I'm approaching this y value of 2 on g of x. And I am approaching that y value of 2 from above 2. I'm approaching it from numbers greater than 2. So that means when I come over to the graph of f, I'm going to approach my value of 2 from numbers greater than 2, which is from the right side. And I can see that that value is 1. So I'm actually able to evaluate this limit, not using the composite rule, but just using one-sided limits, and I see that the value is going to be 1. Question number 37 is again another composition, g of f of x. So it looks a lot like number 36, except for the g and the f are switched around. So the first thing I have to do is evaluate the limit as x approaches 2 of the inner function, which this time is f of x. And I see as I approach an x value of 2 on the graph of f of x, because I'm heading toward two different y values from the left and from the right, that this limit does not exist. And that's as far as I can go with this limit question. If that first limit doesn't exist, then I have no workaround for this. We just say that the final answer of this one is just does not exist. In question number 38, I'm asked to determine the limit as x approaches 0 of f of x. Notice this is a general limit. We talked about this in limits number 1. Let me just remind you what has to be true for that general limit to exist. So what we said is we know it's a general limit because there's not a little plus or minus on that c in that exponent position. So this is our general limit. And what we have to do for that general limit is we have to look at the limit as x approaches c from the left. We have to look at the limit as x approaches c from the right. And those two numbers must be the same value. And then that becomes the answer to the general limit. So let's see how that applies for number 38. So what I see in my function f of x is it looks like x squared plus 4 on the left side of 0, and this cosine function on the right side of 0. Notice that my function is not even defined at 0, but if you recall that general limit, it doesn't matter what happens at the 0. That's more concerned with continuity, but not the limit itself. So I'm going to start by doing the one-sided limits. So here's my limit as x approaches 0 from the left. And on the left side of 0, it's the x squared plus 4 function. I want you to pay attention to the notation I used right here. I did not put f of x right here. I put the specific function that is on the left side of 0. And now to evaluate that function, I am just going to do a substitution. And I just take that 0 and I plug it in for the x, and I get that this limit value is a 4. And again, I use good notation when I do this right side limit. X approaches 0 from the right, that's what the little plus is. So I come up here and I write this specific function. Notice I did not write f of x right here. I wrote the specific cosine function. And now to evaluate this function, I'm going to take my 0 and I'm going to plug it in for my x. And this becomes 4 cosine of 0. And the value of the cosine of 0 is just 1. So this is just has a value of 4. And now I see that my left-hand limit and my right-hand limit were the same value, which means that is my general limit value as well. And so here is my general limit, and that answers the question. And again, I just want to call your attention to the notation. Notice that I put f of x here when I was talking about the general limit because it is a combination of both of these, one from the left and one from the right. Let me give you an example of something that would be bad to write. So the way that I wrote this one in yellow, the limit as x approaches 0 equals 4. That is bad notation because I have to put some function right here, whether it's the name of a function like the f of x, or whether it's the explicit function like I have on those one-sided limits. But just to leave a blank right here is bad notation, and that will cause a deduction. So this one is bad. The next three questions, 39, 40, and 41, are all about continuity. So just a reminder of this three-part definition of continuity. So part 1 says the function must be defined at my value in question. Step number 2 says the limit as x approaches that value must exist. And step number 3, which is at the heart of continuity, is that whatever you get for number 1 and whatever you get for number 2, those two values have to equal. So the value it looks like you're going to hit when you get to A needs to be the actual value you hit when you get to A. So when I look at question number 39, I can see that step 1 holds. F is defined at my x equals 1. At step 2 is where all the work is going to show up for us on this one. So I need to ensure that the limit as x approaches a of f of x exists. So the value that it looks like I'm heading for from the left side and the right side need to equal one another. So my limit value from the left has to equal my limit value from the right. From here, I'm just going to use direct substitution to evaluate these limits. So notice I just plugged the 1 in for the x in each one of these. And when you evaluate a limit, when you do that direct substitution, that's when you drop that limit notation. And I end up with this equation here. And now I just solve this equation for k. And when I do that, I end up with my final answer of k equals -5/4. My function for number 40 looks a little bit different, and all I'm going to do is run through these 3 steps of continuity. Step 1 is the function value at x equals 3, and I see that that value is k. Step number 2 is to ensure that the limit as x approaches 3 exists. So when I look at h of x, it is equal to k when x equals 3. Any other time, whether I'm on the left or the right side of 3, I'm following this function. So I don't necessarily have to do a left-sided and a right-sided limit because this is the function that applies whether I'm on the left or the right. So I'm going to jump straight to that general limit. And when I go to evaluate this, I do a direct substitution first, and it gives me the 0/0, which is indeterminate, so I have to find another way to solve this. And what I see is that this numerator is factorable, so I'm going to go ahead and factor it. And once I factor, I see I have this common factor and cancel it out. And once I cancel that factor out, I can now take my 3 and substitute it in, and I get an answer to this limit is 8. Now step 3 just says whatever you get as your answer to part 1 and whatever you get as your answer to part 2, those 2 things need to be equal to one another. So my step 3 is just doing that. And I get an answer of k equals 8, and that's my value of k. Question 41 is a lot like 39. You just have to do it twice. So this graph of h of x has 3 pieces. One of the connections is happening at x equals 3. And the other connection is happening at x equals 7. So I just need to ensure that the pieces connect at each of those junctures. So the first thing I'm going to do is just pay attention to what's going on here when x equals 3. And I'm just going to dwell on step 2 here, and I'm going to make sure that the y value as I come from the left of 3 equals the y value as I come from the right of 3. And I get this equation, and I'm just going to evaluate each one of the limits. So I'm going to take my 3 and plug it in for each one of these x's. And that gives me this equation. And this is nice because I just have a single variable. So I just go on and I solve for j. And that gives me a j value of 7. And now I just do the same thing at x equals 7. So I'm going to look at the limit as I approach 7 from the left and as I approach 7 from the right. So I'm going to focus on that part that I circled in red. And it gives me this limit statement. And now I just evaluate this by doing direct substitution. So that 7 is going to go in place of each of these x's. And once I do that, I see I have an equation in only a variable of k, so I just go on and solve this equation. And when I do that, I see I get a final answer of k equals 4/3. So this question was nice because j and k didn't depend on one another. I could solve for each one of them separately. Question number 42 is asking us to prove that function f of x is continuous. And you will have a question like this on your free response part, just like you did on the quiz. And if you feel like this is a very particular nitpicky thing, well, you'd be right. It actually really is. So we're going to follow these 3 steps of continuity. Step number 1, I have to make sure that f of a, in this case my a is 0, that f of 0 is defined. And when I do f of 0, I can see that when x equals 0, I follow the top piece of the piecewise, and that gives me a value of 3. So f of 0 is defined and its value is 3. The next thing I have to do is verify that the limit exists. Since I have a piecewise function, I'm going to have to check out the piece on the left, the piece on the right, and make sure they match in order to say that this general limit exists. when I do this, so here's my left-hand limit, and I'm going to choose this piece. And notice I didn't write f of x right here. I actually wrote that to x squared plus 3. When I go to evaluate that limit, I'm just plugging a 0 in, and I get that that value is 3. So my left-hand limit is 3. My right-hand limit, as I approach 0 on the right, I'm going to use that e to the 2x plus 2 as my function. I plug a 0 in. This is e to the 0, which is 1, plus the 2 gives me a right-hand limit of 3 as well. And since these two match, I know that my general limit is 3 as well. And then my last step, step 3 over here, is just to verify that steps 1 and 2 gave the same answer. And we say that like this: the limit as x approaches 0 of f of x equals f of 0. So the value it looks like I'm going to hit as I approach 0 from either side is actually the value that I hit when I get to 0, is what I'm saying in step 3. And then my last step is just to sum all of this up. And I do that simply by saying, therefore, that's what the 3 little dots mean, f of x is continuous at that point in question at x equals 0. In question number 43, I'm given f of x as a continuous function. I'm given some values on that function, and I'm asked to use the IVT to show f of x has a 0. So first of all, what it means for f of x to have a 0 is that f of x takes on a value of 0 at some point on this interval. Basically, what the IVT says is if my function is going to go from a y value of -1 to a y value of 5, I am guaranteed to hit every single y value in between -1 and 5, and 0 just happens to be one of those values. So it's easy to convince yourself that this is a true statement, but just make sure you include all the components when you're using the IVT. So the first thing is to say you have a continuous function. The next step is to position this 0 in between your two given y values. And then I'm going to mention that I'm going to use the IVT. And then I just draw my conclusion, which is basically just restating the question up here. So again, the important components: acknowledge that you have a continuous function, position your number in between the two given y values, mention the IVT, and then draw your conclusion, which is pretty much just restating what the original question was asking. So our last question deals with the squeeze theorem. And what I'm asked to do in the question is to find the limit as x approaches 1 of h of x. And h of x is this squiggly green one that's going in here. And I can see just from the graph that that limit is going to equal 1. But I'm asked to justify it, and that's where the squeeze theorem comes in. So the first thing I have to make sure of with the squeeze theorem is that h of x lies in between f of x and g of x. So when I look at this graph, f of x is the line, so it's the blue one, and g of x is the red one. And what I can see in my graph is that g of x is always the upper bound. It's always above the green graph, and f of x is always below it. So that leads to this inequality right here. F of x is less than or equal to h of x, and that's less than or equal to g of x, and I can just see that in my picture. And I'm trying to find the limit as x approaches 1 of h of x, so I'm going to do the limit as x approaches 1 of each of these three functions. So I've written the limit notation for each one of these three functions, and now I'm going to put the explicit functions in for the f of x and for the g of x. And then to evaluate the limits, I'm just going to do a direct substitution. So in place of the x, I'm going to throw in a 1. And what I find is that each one of these limits equals 1. So this, I just plug the 1 in, and that is just a 1. And this one, when I do 1 minus 1, I get a 0, and e to the 0 is 1. So if you just think about this from a common sense standpoint, if this limit as x approaches 1 of h of x is in between 1 and 1, then it has no choice but to be 1 as well. So h's limit as we approached 1 was squeezed in between f's limit and g's limit. So by the squeeze theorem, I know that the limit in question that I was looking for will also equal 1.